So welcome back to yet another lecture of signals and systems. So in the last few lectures, we have discussed about the Fourier series representation of continuous time signal and as well as the discrete time signal. And you have noticed that this Fourier series is applicable whenever the signal is periodic in nature. So for example, if you'd like to represent any continuous time periodic signal x of t, the corresponding Fourier series representation can be represented as k going from minus to plus infinity x of k multiplied with e to the power j k omega naught t, where omega naught is the angular frequency given by twice by f naught. F naught is the Hertz frequency, that is equal to twice pi by t naught, and t naught is the fundamental period of the periodic signal x of t. So that is basically the Fourier series representation of any continuous time periodic signal. Now what about xk there? This xk is the weights assigned to the kth complex exponential. So we have like infinite number of such complex exponential signals e to the power j k omega naught t, and xk is the weight assigned to the kth complex exponential. Or in other words, we can also assume that this xk is nothing but the component of this e to the power j k omega naught t. Now in the last lecture we have also introduced the notion of the inner product between two signals, or rather two vectors. So what does this inner product infer? This inner product, suppose we have one particular vector and we have, say, let it be, say, let me consider one particular vector is there, let it be u, and we have another vector, let it be v. So whenever we calculate the inner product between this u and v, let's assume that this u is the unit vector and this the v is another vector over there. So when you calculate the inner product between this u and the v, what does it give us? This inner product will provide us, if I calculate the inner product v comma u, that gives us the component, of the vector v along this unit vector u. And we know how to calculate this one. So similarly here, this x of k is nothing but the component, the weights assigned to the complex rotating phasor e to the power exponential complex rotating phasor e to the power j k omega naught t. So similarly, we can find it out, this x of k, because since it is a component, so that gives you this particular representation x of k. Since this is the component, so this component can be calculated by finding out the inner product between the signal x of t and e to the power j k omega naught t. So since x of t is periodic in nature, so instead of integrating from minus to plus infinity, we can integrate from 0 to t, then x of t, and then e to the power j k omega naught t bar dt, which is equal to 1 by t integration over 0 to t x of t e to the power minus j k omega naught t dt. So these two equations, x of t is equal to summation k is equal to minus 2 plus infinity x of k e to the power j k omega naught t, is known as the Fourier series representation of the signal, periodic signal x of t, where x of t is a continuous one. And these Fourier components x of k can be obtained from the second equation, that is x of k, which is given by 1 by t 0 to t x of t e to the power minus j k omega naught t dt. Now this particular representation is known as the exponential Fourier series representation, because we have represented the signal x of t as the weighted addition of complex exponential signal. Now sometimes for the real signal, it is also useful to represent the signal x of t by virtue of some trigonometric form. So instead of representing this one by e to the power j k omega naught t, it is also useful to represent in this particular form. Some DC component is there, which consists of zero frequency. So basically we have like the in this particular summation extends from minus to plus infinity. So we are dividing it from minus infinity to minus 1, then 0, and then 1 to infinity in that way. So this A0 is basically the DC frequency or the zero frequency, and then this can be represented like k is equal to 1 to infinity bk cos k omega naught t plus summation k going from 1 to infinity ck sine k omega naught t. So instead of finding out the component of the signal along e to the power j k omega naught t, we are now finding out the component of the signal xt along cos k omega naught t and sin k omega naught t for varying k. So that is a kind of representation. Now the question is that how can I find out these individual components, this A0, AK, I mean A0, BK and the CK over there. Now that is pretty easy. Finding out the values for A0 is not a very difficult job. So this A0, since it's a DC component, this A0 can be obtained if I put K is equal to 0 in this particular expression. Already we know that the formula x of k was something like that, 1 by t integration over 0 to t x of t e to the power minus j k omega naught t dt. So if I simply put k is equal to 0 in this particular expression, we'll be getting what is the value of a0, that is 1 by t integration 0 to t xt dt. So physically what does it signify? 1 by t integration 0 to t xt dt will give us the average value of the signal x of t, because x of t is a periodic signal and a continuous signal, continuous periodic signal. If you simply calculate this one integration over 0 to t xt dt 1 by t multiplied with this, that will give you the average component or average content or the DC content of the signal. So by virtue of this, we can segregate the DC component. Then we have the other component, those components. So now we can represent this x of t as a0. A0 is basically the DC component. Then we have k going from minus to plus infinity, but k is not equal to 0. x of k. Then we have in this expression of Fourier series x of k e to the power j k omega naught t. So this e to the power j k omega naught t we can simply represent like cos k omega naught t plus j sin k omega naught t. Remember that we have already excluded this k is equal to 0 because this k is equal to 0 is represented in a0 only. So that is equal to a0 plus k going from 1 to infinity x of k cos k omega naught t plus k equal to minus infinity to minus 1 x of k cos k omega naught t plus k is equal to 1 to infinity x of k sin k of omega naught t plus summation k going from minus infinity to minus 1 x of k sin k omega naught t. So we have just segregated into 4 different summation k going from 1 to infinity xk cos k omega naught t plus k equal to minus infinity to minus 1 xk cos k omega naught t plus k going from 1 to infinity xk sin k omega naught t plus k going from minus infinity to minus 1 xk sin k omega naught t, but we have left one j part over there, so this j has to be there outside, so this should be jxk, right? Okay, so now moving forward, this can be written like small one, so that is equal to a0 plus first summation we can keep it as it is k equal to 1 to infinity xk cos k omega naught t, and in the second summation what we have, the second summation ranges minus infinity to minus 1 x of k cos k omega naught. So if I just replace k with minus m, then I can simply write like this: k is equal to 1 to infinity x of minus k cos x of minus k cos k omega naught t, because cos is an even function. Then we have the two terms for sine as well. So k is equal to 1 to infinity j times xk times sine k omega naught t, and then since sine is an odd function, so we should have a minus over there. K is equal to 1 to infinity j x of minus k sin k omega naught t. Now combining the second and third term, what I can get, a0 plus summation k going from 1 to infinity x of k plus x of minus k cos k omega naught t plus k going from 1 to infinity j times xk minus x of minus k sine of k omega naught t. So actually in our representation, what we have got like x of t must be represented like a naught plus k is equal to 1 to infinity bk cos k omega naught t plus summation k equal to 1 to infinity ck sine k omega naught t. Now we have got almost the same form. Now we have to identify what is the ak and what is the bk, what is the bk and what is the ck value over there. So we can readily identify that this bk in the representation the bk value in the representation is given by x of k plus x of minus k. So if I know the components or weights for the exponential Fourier series representation, so from that we can easily calculate the weights for the trigonometric Fourier series representation by virtue of this one, bk is equal to xk plus x of minus k. And what about the ck? Ck is equal to j times xk minus x of minus k. So by virtue of this, we can establish the relationship between the complex exponential Fourier series representation and trigonometric Fourier series. Now the question still persists that how we can get back this bk and the ck, because here bk are the corresponding weights against the cosinusoidal term and ck are the corresponding weights for the sinusoidal term. So how can I get back those values? Because already we have got the ak expression, I mean this this xk expression over there. This xk was written like 1 by t integration 0 to txt e to the power minus jk omega naught t. So if I follow the same procedure over here also, we will be able to find out the expression for bk and the ck. So we have noticed that bk is given by x of k plus x of minus k. So what was x of k? As simple as 1 by t integration over 0 to t, that is the component of x of t along this complex exponential signal, it is equal minus jk omega naught t dt plus 1 by t integration over 0 to t. Now here we have x of minus k, so we have to replace k with minus k, so x of t e to the power j k omega naught t dt. Now if we club them together, integration interval is the same, 0 to t over there also, over here also. Xt is common. Now in one hand we have e to the power jk omega naught t, in other hand we have e to the power minus j k omega naught t. So if you club them together, that will give us 2 cos k omega naught t. So that is basically 2 by t integration over 0 to t x of t cos k omega naught t dt. Next is how to find out the ck. The ck value follows the same procedure of calculation, that is j times x of k minus x of minus k. That will give us j by t integration over 0 to t x of t e to the power minus j k omega naught t dt minus j by t integration 0 to t x of t e to the power j k omega naught t dt. Now if you do simple mathematical substitution, we'll readily find out that this value turns out to be 2 by t integration over 0 to t x of t sine k omega naught t dt. So by virtue of this, we are able to find out the relationship between the exponential Fourier series and the trigonometric Fourier series and the corresponding coefficients like xk, bk, ck, how are they related, how are they connected. We are also able to find it out. Now before I conclude this lecture, I would like to point out at a very important phenomenon regarding the behavior of the signals in the time domain as well as in the frequency domain. So in the time domain, as you know, the signal could have been in the time domain, there could have been two different properties for the signal, two different characteristics of the signal. One is the signal can be continuous. Let me use a different color. Time domain signal can be continuous or it can also be discrete. Signal can be continuous or it can be discrete also. That is one aspect of the signal, either continuous time signal or discrete time signal, as far as their appearance is concerned. And as far as their repetition is concerned, it can be periodic or it can also be aperiodic. Similarly, in the frequency domain, so it can be periodic as well as aperiodic or non-periodic. Aperiodic or non-periodic. Similarly, in the frequency domain, if I like to observe the behavior of the signal in the frequency domain, what we have, the signal can be discrete as well as it can be continuous. whenever we have observed the signal representation in the frequency domain, so it can be discrete as well as it can be continuous. So here we write discrete or continuous. And as far as the periodicity is concerned, it can be aperiodic as well as periodic. So these are the different aperiodic as well as periodic. So by virtue of this, we have created one table. In the time domain, signal can be continuous, discrete, periodic or aperiodic. In the frequency domain, signal can be discrete, continuous, aperiodic and periodic. Now, depending upon the quality of the signal in the time domain or the appearance of the signal in the time domain, we can readily identify what should be its appearance in the frequency domain and what type of analysis we are going to perform. So, for example, we have already mentioned that this Fourier series representation is applicable whenever the signal is periodic in the time domain. So if the signal is periodic in the time domain, so time domain, in the time domain, if the signal is periodic, then only we can go for the Fourier series analysis. It can be a continuous time Fourier series if the time domain signal is a continuous one, and it can be a discrete time Fourier series if the time domain signal is a discrete one. But as far as the signal is periodic in the time domain, we always go for the Fourier series representation. So accordingly, we can write it down. This Fourier series representation or continuous time Fourier series, typically it is called a simple Fourier series representation. This Fourier series representation is applicable whenever the signal is continuous as well as periodic. And if it is discrete and periodic, then we go for a discrete time Fourier series. Typically, the continuous Fourier series, whenever we call it like Fourier series, it implies that it is continuous time Fourier series, a CTFS, if nothing is mentioned. Otherwise, if the signal is discrete, then it should be categorically mentioned as discrete time Fourier series. Now, whenever we consider the signal in the time domain as a periodic signal, then we can go for either Fourier series or continuous time Fourier series or discrete time Fourier series, depending upon the time domain representation of the signal. Now, what about its corresponding frequency domain counterpart? We know that for a continuous time Fourier series representation, we can have infinite number of such complex exponentials, this e to the power jk omega naught t, and there is no such repetition. We can have infinite number of such harmonics. So e to the power jk omega naught is the fundamental frequency, and then we have all the harmonics k omega naught, first harmonic, second harmonic, third harmonic, fourth harmonic, so on and so forth. So in the frequency domain, this is aperiodic in nature, and this is discrete. So that's why we have used like summation. So in this expression, we have written like summation k is equal to minus 2 plus infinity xk to the power jk omega naught t. The signal is continuous and periodic in the time domain, and the frequency domain, its representation is something like that. There is no integration, there is a summation. That means in the frequency domain, it is discrete in nature. And this exponential, this complex exponential, it is by jk omega naught t. These are aperiodic in nature. And that can be easily verified from here. Fourier series is applicable when that signal is time domain In the time domain, the signal is continuous and periodic, and in the frequency domain, this is discrete and aperiodic. On the other hand, if I consider the discrete time Fourier series, in that case, we know that we can also represent signal like x of n is equal to summation x of k e to the power j k omega naught n. But remember, that time the summation doesn't go from minus to plus infinity, rather it goes from 0 to n minus 1, because this e to the power j k omega naught n, this complex exponential, this is n periodic, there is repetition, this is n periodic. So therefore, whenever the signal is discrete and periodic, we go for discrete time Fourier series. And then in the frequency domain, this is periodic as well as discrete. Why discrete? Because we have like summation k is equal to 0 to n minus 1. So we have only discrete such frequency components. And remember, these discrete frequency components are periodic in nature also. This is n periodic. And the rest two part that I have not filled yet, when the time domain signal is aperiodic, whether it be continuous or discrete. So over here, we will be using different types of representation of the signal that we have not covered yet. So with this, I would like to conclude this lecture.